Hello, everybody, and welcome back. Today we're going to be doing section 6.5, and this is where we're going to start to get a whole bunch of trigonometric identities. We're going to start with the sum and difference identities and formulas for sine and cosine and tangent, and then we'll work from there in the other sections. Let me pull up the slides and we'll get started. All right, so first an overview. We're going to start with the sum and difference formulas for cosine, and then we'll get the sum and difference formulas for sine, and then we'll get the sum and difference formulas for tangent, and then we'll do just a few more examples after that. One second. There we go. Okay, so first let's look at the actual statement of the theorem. So let's say you've got two angles, alpha and beta. Alpha and beta are just real numbers, they're angles. Then the following identities hold. We have that the cosine of alpha plus beta is equal to cosine alpha times cosine beta minus sine of alpha times sine of beta. And then cosine of alpha minus beta is a little bit different. It's cosine alpha times cosine beta plus sine of alpha times sine of beta. One thing I want to emphasize here that I mentioned earlier as well, you will not need to memorize these two formulas. I know some other instructors like to have you memorize these, but I don't find that to be too fruitful. If you ever need these particular formulas, you can always look them up. And another reason why I don't like to have students memorize these formulas is because the formulas for sine and cosine are very, very similar. They're pretty much the same, except the cosines and sines are switched, and the actual like signs, plus or minuses, are switched. So it becomes very treacherous, you could say, to try to memorize them all, because if you forget one little detail, then you don't have the right identity. But I'll be very clear about which ones you do need to memorize, because we're going to get all of those in the next few sections. But on that note, let's prove one of these first. And what's really cool is only one of these identities that we get has a geometric proof. And then all the other ones that we're going to get just follow from previous identities that we've proven. So we're actually going to prove formula 2. And then from formula 2, we're going to get formula 1, and then we're going to get all the sum and difference formulas for sine, cosine, tangent, and so on. It's pretty cool. So we will do this proof. Uh, First thing we're going to do is we're going to assume that our angles alpha and beta are between 0 and 2 pi, and we're going to assume that alpha is less than beta. This holds true for any angles alpha and beta, so we don't need to make this assumption, but it'll just make the proof a little bit easier to follow in this case. All right, so let's take a look at these two pictures. What I'm going to do is zoom in a bit, talk about some of the pieces. So first we have the angle alpha right here, right? So that's the angle that's the angle from the x-axis to this ray right here, right? So that's the angle alpha. And then here's the angle beta from the x-axis to this ray right here. And so from that, we can actually see the angle alpha minus beta. So the angle alpha minus beta is right here. So this little space right here is alpha minus beta. And what we would like to find out is the cosine of that angle. So a couple things that we know right away are this. So if this is the angle beta, then this point right here, that's the point cosine beta, sine beta, just by definition of cosine and sine, right? We're on the unit circle. So on the unit circle, if you have a point on it, the location of that point is cosine of that angle, comma, sine of that angle. So that's what this is. That's where that point lives. And then this point lives at cosine alpha, sine of alpha, right? So that's the setup so far. We're going to call this point P2, and we're going to call this point P1. Okay, now here's where we're going to be a little bit clever. We're going to take this entire image and we're just going to rotate it by an angle beta so that this ray coincides with the x-axis right here. And that's the next figure. So it's still the same triangle. The triangle is congruent to the one we were working with right here, this triangle. It's just been rotated so that this edge lies along the x-axis instead. That's what's going on there. Well, the reason this is handy is because now we know that this is the angle alpha minus beta still. But now we've put these points in a better position for us to analyze what's going on. So first, this point now lies at the coordinates 1, 0. And then this point, by definition of cosine and sine again, is cosine of alpha minus beta and sine of alpha minus beta. All right, so this is like point number 3, right? Now here's the idea. What we know from these two pictures, I'm going to zoom back out again, is that this distance right here, is equal to this distance right here. There's no difference between those two lengths. It's the same side of the triangle, it's just been rotated. So those two distances are the same. In particular, the distance between the points P1 and P2 is the same as the distance between the points A and P3. And so that's what we're going to use to derive the identity. We're going to use that equality that I just mentioned out loud. So let's take a look at what it is. So like I just mentioned, this distance is equal to this distance. And from that, we're going to get the identity, as you can see at the bottom here. Let's see how it falls out. So first, we're just going to use the distance formula. So nothing too special there. It's just the good old distance formula that you love and remember from earlier on. That's what this is right here. That's the distance between those 2 points. And then this is the distance between those other 2 points. And we're just filling in what we know about the coordinates, the x and y coordinates, right? So remember, this would be like, this would be like x2, and this would be x1, this would be y2, and this would be y1. Because remember that second point P2, is lying at the point 1, 0. 1, 0. So that's what you're looking at right here. And then you do the same thing over here. This is x2, x1, x2, x1. And then we're just going to kind of massage things and simplify things, expand things and combine things, and everything kind of washes out. So here we go. First step is you can square both sides. And once you square both sides, you can get rid of those radicals, and then you're just left with that. And then the next step, to go from here to here, it's just good old FOILing out, good old distribution. Multiply everything out, use the FOIL method or just distribution if you want to think of it that way, and just do the distribution for each one of these powers that you see right here. And when you do that, you get a very long, very, very messy equation. So here's the right side of the equation, and then here's the left side of the equation. I'm sorry, the left side and then the right side, my bad. All right, now what you can do is you can go simplify a few things. You've got some things that are going to end up equaling 1. So for example, let me highlight these. Look, we've got cosine squared alpha minus beta and sine squared alpha minus beta. Well, by the Pythagorean identity, that's equal to 1. So that just becomes 1. And that's when we combine it with this 1, that's where we get 2. And the same thing happens on the other side. So here we've got cosine of alpha. Actually, let me clear this up. We've got cosine squared alpha and cosine squared, oops, sorry, not that one, sine squared alpha. That's going to add up to 1. Then we've got cosine squared beta, sine squared beta. That's going to add up to 1, right? And so then what's left is 2. And then these two things right here, like so. All right, so clearing all that out of the way, now we can look at the second to last step. So in the second to last step, we have this result right here. And the first thing we can do is we can cancel the 2's. So these 2's will cancel. Then we can divide everything by -2. So if you divide everything by -2, those will disappear. And then voila, you're left with cosine of alpha minus beta equals cosine alpha cosine beta plus sine alpha sine beta. Hooray! That's the proof of the first formula. One note I'll make here, since we just finished this proof, the utility of this identity and the utility of this formula is that you can compute the value of this, the cosine of this angle difference, just by referring to the individual angles that you're starting with. That's the utility of an identity like this. It kind of simplifies things. But now we're going to do something a bit clever. So we got formula number 2. Now let's get formula number 1. So here we go. This is going to be much, much quicker. So we already proved that identity. We proved this. This is now free for us to use. This is a tool. We can use it whenever we want. So we're going to use it right now. Formula 1 is just going to follow from the even and odd identities and the clever fact that alpha plus beta is equal to alpha minus negative beta. That's how we're going to do this. So here we go. Here's the clever part. We're going to rewrite cosine of alpha plus beta as cosine of alpha minus negative beta. But just a moment ago, we proved an angle difference formula for cosine. So we have an identity and we have another expression for cosine of alpha minus negative beta. And it's this. It's this right here. So that's just using the identity we just proved. Then the last thing you got to remember is that cosine is an even function. So cosine of negative beta is just equal to cosine of beta. And then sine is an odd function. So sine of negative beta is negative sine of beta. And then from that, we get the angle sum identity for cosine. There it is. Woohoo! And then that's the end of the proof. So now we've got an angle sum identity for cosine. We've got an angle difference identity for cosine. Let's just use it and see how we can use it. So here's an example. Find an algebraic expression for cosine of 75 degrees. Now, 75 degrees isn't one of the standard angles, so it's not a value that we can just see outright. You know, it's not like root 3 over 2 or root 2 over 2. It's some other value. 75 degrees is not standard, right? But if we can rewrite the number 75 in terms of other standard angles, like a sum or a difference of standard angles, then we can use that angle sum or difference formula to compute cosine of 75, or at least convert it to an algebraic expression. So let's try it here. So after a little bit of thinking, you might be able to recognize that 75 is equal to 45 plus 30. And that's great, because 45 and 30 are standard angles, and we know the cosine and sine values of those angles. So since we have an angle sum going on, we're going to use the angle sum formula for cosine. That becomes this right here. And then now we can just compute those cosine and sine values at the standard angles. So cosine of 45 is root 2 over 2, cosine of 30 is root 3 over 2, sine of 45 is root 2 over 2, sine of 30 is 1/2. And then now everything is algebraic, there's no more trigonometric function involved, and then you can just kind of simplify things. There we go. So what we just showed is that cosine of 75 degrees is equal to 1/4 of root 6 minus root 2, which is cool. So now we have an algebraic version of this value. One little note I have at the bottom here, the book phrases this as finding the exact value of cosine of 75 degrees. I just prefer to call it finding an algebraic expression, mainly because technically this symbol right here is the exact value of cosine of 75 degrees. But this might be a little more handy depending on what you're trying to work on, right? Because now we can express it completely without any trigonometric functions. We can express it purely through algebraic functions like a radical function. All right, let's see another example. Let's prove these identities. So now this is something we had seen earlier on. These identities right here, they're essentially saying that cosine and sine are shifts or translations of one another. Because if you shift by pi over 2, you end up getting the other function, right? So if you shift cosine by pi over 2, you get sine. If you shift sine by pi over 2, you get cosine. Well, now that we have the angle sum and difference formulas, we can prove that directly. So here we go. We're going to be a little bit clever again when we get to this part right here. But to start, we're just going to use the formulas. So cosine of pi over 2 minus theta. Actually, I'll go back to my laser here. Here we go. Cosine of pi over 2 minus theta. Use the angle difference identity, and we get this, and this. There we go. Then we just evaluate them at the angles that we know. Cosine of pi over 2 is 0. Sine of pi over 2 is 1. And so then you're left with 0 plus sine, which is sine of theta. There we go. Now, we're going to use this result. It's like this daisy chain of results, right? Now we're going to use this result to derive the other identity. So what is sine of pi over 2 minus theta? Well, we're going to be a little bit clever, and we're going to write it as pi over 2 minus pi over 2 minus theta. Pi over 2 minus pi over 2 minus theta. That's what we're going to get. And then now we can use this result right up here. So now, let's see, where did it go? Where did it go? Oh, geez, where is it? Sine of, where did it go? Oh, there we go. Okay, so this pi over 2 here is this pi over 2 right here. That's what it is. That's what it is. All right, next. Oh yeah, okay, so now we can prove the other one. If you shift the other way instead, then you're going to get sine of theta again. So this one is similar. You're going to use results from the previous example and the even odd properties of cosine. And here what you can do is you can rewrite this angle, theta minus pi over 2, as negative pi over 2 minus theta. This is actually a pretty common technique in mathematics. We're basically taking this expression and we're factoring out a -1. So we're getting negative a plus b, but then this can be rearranged to be negative b minus a. So in other words, a minus b is the same as negative b minus a, and that's what you get right there. That's what we're using here. All right, but then remember cosine is an even function, so cosine of a negative angle is just cosine of a positive angle. And then previously we just proved that cosine of pi over 2 minus theta is sine of theta. There we go. All right. Now let's talk about sine. So there are sum and difference formulas for sine as well. Here they are. So no matter what two angles you're given, alpha and beta, we have that sine of alpha plus beta is sine of alpha times cosine beta plus cosine alpha times sine beta. And then sine of alpha minus beta is very similar. The only difference is you're going to change the sign in between the two terms. And that's pretty much it. That's pretty much it. Now, what's interesting here is we're not going to have to make a geometric argument for this. You could actually, you could refine, or not refine, you could revise the argument we made earlier to compute the difference formula for cosine, and you could get these as well. But we don't need to do that. We can just use what we already know about cosine and sine to derive these identities algebraically. So here we go. What is sine of alpha plus beta? Well, we just proved a moment ago that that's the same thing as cosine of pi over 2 minus whatever angle you put in there, pi over 2 minus alpha plus beta. Then we can kind of shift things around. We could apply this negative to both terms here, and then just notice that we've got pi over 2 minus alpha minus beta. And then if you kind of squint your eyes and don't look at the individual terms inside of each expression, you can see that what we've got is cosine of an angle minus another angle. So we have a difference, right? So cosine of a difference, we got a formula for that. And so now we can plug that into the formula. This. And that's using formula number 2 from the first couple slides. All right, clever results. Now the last step is the other thing. So remember that cosine of pi over 2 minus alpha is the same as sine of alpha, right? So if you have that shift, or really I should say reflection in a shift, you're going to get the sine function. Similarly, sine of pi over 2 minus alpha, that's going to give you cosine of alpha. So using those identities, we get the one we were trying to prove. Sweet. So now we've got angle sum and difference for cosine, we've got angle sum for sine, and then maybe not surprisingly, we're going to get the angle difference for sine pretty quickly here. We're just going to use the same technique as before, write alpha minus beta as alpha plus negative beta, and then use the even odd properties of sine and cosine to get this. There we go. All right. Now what are we going to do? Let's play for a minute. Let's practice using this and see if we can do something similar to what we did with cosine. Let's find an algebraic expression for sine of 7 pi over 12. And just like before, there aren't any standard angle, or 7 pi over 12 is not a standard angle, so we can't just evaluate this outright. But if we can think about how to rewrite 7 pi over 12 in terms of standard angles that we know, then we'll be able to evaluate sine and cosine at those angles. So what I want you to do is take a moment now and see if you can think about how to split up 7 pi over 12 into two angles that are standard angles, either a sum or a difference. How would you split that up? All right, let's see one way to do it. So if you notice that 7 pi over 12 can be written as 3 pi over 12 plus 4 pi over 12, you might notice that those reduce to pi over 4 and pi over 3. Well, that's great because pi over 4 is a standard angle and pi over 3 is a standard angle, so we can use the formulas that we just derived to write this in an algebraic form instead. So just like we did with cosine, we're going to rewrite sine of 7 pi over 12 as sine of pi over 4 plus pi over 3, and then we're going to use our angle sum formula for sine. Now we're going to evaluate each one of these standard angles, or evaluate sine and cosine at each one of these standard angles, and then we're going to get algebraic versions of each one of those values. And then that's it. So 1/4 root 2 plus root 6. All right. Okay, so what's next? Let's try this example. Let's say that we know that sine of alpha is 4 over 5, and we know that alpha is in the second quadrant. So alpha is between pi over 2 and pi, right? So you can think about the unit circle. We're over here somewhere. Alpha's over there somewhere. We're also going to suppose that sine of beta is equal to this value right here. So we know what sine of alpha is, and we know what sine of beta is. We also are given that beta is in the third quadrant. So if you think about the unit circle, beta is down here somewhere between pi and 3 pi over 2. Using this information, let's find an algebraic expression for sine of alpha plus beta, and we'll be able to. One thing we can think of right away is we're going to use the angle sum formula. But what I want to do is pause for a minute, and I want you to think about how you could use this information to figure out how to find sine of alpha, sine of beta, and cosine of alpha and cosine of beta. So think about it for a minute, and then we'll do it together. All right, now let's try this together. The good news is this: if we know what sine of alpha is and we know what sine of beta is, we can use that to figure out what cosine of alpha and cosine of beta are. Because remember, sine is the same thing as, where is it? Here we go. There. It's the same thing as a vertical displacement divided by the hypotenuse, right? The radius of that circle. So from that, we can figure out what cosine is. Here we go. Cosine of alpha using the Pythagorean identity is going to be this. But we have an expression for sine of alpha. So within this radical, we know what sine of alpha is. Sine of alpha is 4/5. So 4/5 squared is 16 over 25. And then we get this once we simplify. So remember, whenever you're taking a square root of something, you always have to include a plus minus. And then you have to eliminate a case, perhaps, depending on the context of the problem. This is why we had that other information, because we don't know immediately if we need to take negative 3/5 or positive 3/5. But remember, they said that angle, the angle alpha, oops, come here, there you go. The angle alpha is in the second quadrant. So if we're in the second quadrant, over here, cosine is negative over there. So that means we need to take the negative result. So from all of this, oops, there we go. We're going to get that cosine of alpha is negative 3/5. All right, now let's do a quick survey. We know sine of alpha, we know cosine of alpha. We know sine of beta, but we don't know cosine of beta yet. So we're going to use the exact same argument to find cosine of beta. And that's right here as well. Again, we're going to end up with plus or minus. We don't know which to choose yet, but they tell us that angle beta is in the third quadrant. Cosine is negative in that quadrant, so we're going to take the negative result. And now we've got everything we need: sine alpha, sine beta, cosine beta, and now we can use the angle sum formula and get an algebraic expression for that value. There it is. Pretty cool. It's nice how it all fits together like that. All right, moving right along. Now we're going to get the sum and difference formulas for tangent. So setup is before. Let's just say you've got any two angles, alpha and beta. Tangent of alpha plus beta is going to be given by this expression here. And then tangent of alpha minus beta is going to be given by this expression right here. So again, very, very similar. The only difference is these signs change. These signs change. All right. And then now let me ask you, think about this for a minute before we do the proof. How do you think we're going to get these sum and difference formulas? What do you think we're going to use? All right. If you said we're going to use the sine and cosine formulas, you're right. That's basically what we're going to use. Let's go right to this. So remember, the definition of tangent is sine over cosine. So tangent of alpha plus beta is sine of alpha plus beta over cosine alpha plus beta, just by definition. And from that, we can use the angle sum identities we got earlier on. And that's what we're doing right here, using those identities we just derived earlier. Now, the next thing we have to do is this. So for one, this isn't a terrible formula on its own, right? It's just the sine and cosine formulas. But the next thing we're going to do is we're going to multiply by a clever 1 just to tweak things a little bit, because it would be nice if we can have this formula in terms of tangents instead of sines and cosines. That way, if you know the tangent of your angles, then you could just use that information instead of having to go to sines and cosines. So here we go. This is the clever 1 that we're going to multiply by. 1 over cosine alpha cosine beta over 1 over cosine alpha cosine beta. This is equal to 1, and we're just going to distribute it to the terms in the numerator and the denominator, this and this. And then after you do that, you get this expression in the numerator, sine alpha over cosine alpha, wink wink. Sine of beta over cosine beta, wink wink. Sine of alpha over cosine alpha, sine of beta over cosine beta, wink wink. That's tangent, right? That's tangent. So tangent alpha, tangent beta, tangent alpha, tangent beta. And that's the proof. There we go. Next, we can use this result to get the angle difference identity for tangent using the same techniques we were using the previous two proofs. We're just going to use the even-odd identities and rewrite the difference as a sum. So that's what I do right here. And then this is the formula. All right. So once again, I just want to reiterate, you do not need to have these formulas memorized. I will provide you with these formulas, but you are going to have 6 formulas in particular memorized, which I think I talk about in the next lecture or possibly the one right after that. But the sum and difference formulas you do not need to have memorized. All right, so let's use this. Now we can actually prove that tangent is pi periodic. That's something that we can prove geometrically just using the unit circle. But now that we have this formula, we can prove it algebraically as well. The proof is really, really quite short. You're just going to use the angle sum identity. And once you plug in the values that you know, everything works out quite nicely. So tangent of theta plus pi is tangent of theta plus tangent of pi over 1 minus tangent theta, tangent pi. Tangent of pi is 0. So we get a bunch of cancellations, and we're just left with tangent theta. So there you go. This is an algebraic proof that tangent is pi periodic. All right, now, how about this one? This one. So how do you think we could figure this one out? Think about it for a minute, and then we'll do it together. All right, so this one is a little bit sneaky, I have to admit. If you said that we're going to use the angle sum formula for tangent, turns out that we actually cannot use that in this case. And the reason is that tangent of pi over 2 is undefined. So tangent of pi over 2 is not an angle that we can evaluate, so we can't use it out, or we can't use the angle sum formula for tangent outright. We're going to have to go back to sines and cosines. And so that's exactly what we're going to do. Since we can't use that tangent formula, we're just going to use the formulas for sine and cosine because they are defined everywhere. They're defined for every angle, right? So here we go. We're going to rewrite tangent of theta plus pi over 2 in terms of sines and cosines, and then just go through the algebra at that point. So we used our identities right here, and then now we can simplify everything using evaluating sine and cosine at the angles that we know. So cosine pi over 2 is 0, sine of pi over 2 is 1, and so on and so on. Do a bit of simplification, and you get that this result is equal to cosine theta over negative sine theta, which is negative cotangent theta by definition. There we go. Another proof. Can do lots of proofs with these. All right, so now what we're going to do is we're just going to do a couple more examples, and then we'll call it a day. So this is a fun one to do. Remember that sometimes we don't really need to see these angles as actual numbers. We can just see them as angles. So let's try to write this expression as an algebraic expression in terms of u and v. And then we're going to provide restrictions on all of these things. So this is one of the reasons why I like to emphasize this notion of algebraic expression. This expression as it is trigonometric. It's got a bunch of trig functions in it. Sine, sine inverse, cosine inverse. Sometimes it is beneficial to rewrite expressions like this that don't involve trig functions, because trig functions can be tricky. They can be tricky to work with, especially because they're transcendental. That's something you'll talk about in Calc 1. So what we're going to do is we're going to find a way to use the sum and difference formulas that we just learned in this section to get a different representation of this expression. So first I want you to think about it for a minute. How could you rewrite this as an algebraic expression in terms of u and v, meaning only u and v appear in your formula, no sines and cosines? So think about it for just a minute. All right, and then let's work on it together. So the first thing that you have to recognize is this. This right here, sine inverse of u, that's an angle. Remember the inverse trig functions, those are angles. So the inverse trig functions give you an angle that have these values right here. So sine inverse of u is the angle whose sine is u. And cosine inverse of v is the angle whose cosine is v. So let's just call them an angle. Let's just call them alpha and beta. Here we go. Do I do that yet? Oh, I do that on the next slide. So this is just what I was saying, right? So this is the angle whose sine is u. This is the angle whose cosine is v. One thing we have immediately, since we were also asked to provide restrictions, is that u and v have to be between -1 and 1. And that's because sine and cosine are bounded by -1 and 1. They lie in between -1 and 1, inclusive, since they're sine and cosine values. Now what we're going to do is relabel those inverse trig functions as just angles. So that's what I'm doing right here. We're going to let alpha be sine inverse of u, and beta equal cosine inverse of v. And then by definition, we'll have that u equals sine of alpha and v equals cosine of beta. So this tells us that alpha's got to be between -pi/2 and pi/2, and beta's got to be between 0 and pi. All right, this might be a little bit tricky, but remember, if you work with inverse trig functions, you have to carefully consider the domains. You have to be very careful with that, and remember that the domains have been restricted to even be able to talk about these things. So if we are saying that alpha is sine inverse of u, implicitly we have that alpha has to be within this interval of angles. Otherwise, we can't even have the inverse trig function. Same thing with beta, right? So in order for cosine inverse to be well defined, we had to restrict the domain to be 0 to pi. So that means that beta is between 0 and pi. Okay, now, because we know these facts right here, this tells us that, maybe I'll start here. Because we know this fact, this tells us that cosine of alpha, oh, sorry, I was right the first time. Because we know alpha is in -pi/2 to pi/2, cosine of alpha has to be non-negative, has to be greater than or equal to 0. Think about the unit circle, right? -pi/2 to pi/2, that's over here. Cosine is positive there, or non-negative there, so we get that result. Similarly, if we look at this instead, if beta is in the interval 0 to pi, that means that sine of beta is positive. Let me draw that right here. Okay, so if we're in this interval, sine is always non-negative, right? So we know this. Why did we need that? Because that's going to help us figure out whether to choose the positive or negative results when we use the Pythagorean identity. And so that's what's going on next. Let me erase this. There we go. Okay, so now when we want to compute what cosine alpha is, we know that we're going to take the positive root. Same thing with sine. We're going to take the positive square root. And then we get two pretty cute results here. Cosine of alpha is equal to this, but we know what sine of alpha is. Sine of alpha is u. So this becomes 1 minus u squared. And we know what cosine of beta is. Cosine of beta is v. So this one down here becomes 1 minus v squared. And now what you can see is that we've eliminated the presence of cosine and sine, and we only have u's and v's. At least for this, we can write cosine in terms of u, and we can write sine in terms of v. Now, how do we write this in terms of u's and v's? Well, what has all this buildup been for? Why have we been collecting all of these pieces for the past couple slides? Well, now the thing to recognize is that this, oops, come back, there you go. This is alpha, this is beta. So what we have is sine of alpha plus beta, and we're going to use the angle sum formula for sine. So here we go. Sine of this stuff is equal to sine of alpha plus beta. Now we can use the angle sum identity that we derived earlier to rewrite this as this. And then now we can just substitute what we know about sine of alpha, cosine beta, and so on and so on. So that's where we get this result. So sine of alpha cosine beta, that's u times v, because sine of alpha is u and cosine of beta is v. And then cosine of alpha sine b, those are those two radicals that we just computed a second ago. There we go. So now check that out. So what we did was we rewrote this expression with no trigonometric functions involved whatsoever. Now the only thing that's involved are algebraic functions, the square root, and just products, right? So that's the benefit of doing it this way. So now we don't even need to talk about trig functions at all. We can just talk about values. And these are identities. Like this is an equality, right? So these two things are equal. They're the same thing, just written in different ways. All right. So on that note, let's play. So now that we've covered this, you should go start the homework. You can read through the book. You can rewatch the lectures. You're more than welcome to read through the slides again and so on. But I think I'll stop there since I've been talking for long enough and I know you got other things you want to do. So I'll see you next time and happy studying.